Hello, Mr. Betts here. We are getting into Unit 3 now, and Unit 3 is kind of a continuation of Unit 2. So back in Unit 2, we learned how to take the derivative using the limit definition, and then we learned a bunch of shortcuts for taking derivatives of certain types of functions. So we looked at categories of functions like polynomials and exponential functions and trig functions and logarithmic functions, and we came up with shortcuts so we didn't have to use that limit definition for these categories of functions. Then we talked about how we could combine those functions by taking derivatives of sums and differences, products and quotients. So using these, we were able to take derivatives of more complicated functions. And there's one more way that we're going to combine functions, and they're going to look more like this. So all of the examples that I have on the screen here, these are all compositions of functions. So a composite function is just when we plug one function into another function. So for example, in the first one here, we have the x cubed function in the sine function. So instead of sine of x, we have sine of x cubed. And if we are able to take the derivative of these composite functions using some sort of shortcut, we should be able to increase the complexity of the functions that we can take derivatives of very quickly and very easily. So let's start with looking at how we would take the derivative of a composite function. And I'm going to look at this using the limit definition. And we saw this with the product rule, with the quotient rule. If we can come up with a shortcut for taking derivatives of composite functions using this limit definition, then we don't have to use the limit definition to actually take those derivatives. So I got a little bit of a start here. So this part here is just the limit definition of the derivative of f of g of x. Then just like I did with the product rule and the quotient rule, I multiplied by a fraction that's really equal to 1, but then we can use that to manipulate it into a form that we can change. So in this step here, by switching the denominators that we had in this step, we got one of these limits. By the way, I split it up into two separate limits with the product, and we can do that as long as both of those limits exist. And we have one of them that is going to be g prime of x. So this should look familiar here. That's just the definition of g prime of x. What we have left over here with this one, though, is not as straightforward, but with a little bit of manipulation and algebraic substitution, we're going to be able to make that look like a different derivative. So what I'm going to do here is I'm going to introduce a new constant. I'm going to call it k, and I'm going to let k equal the denominator here, which is g of x plus h minus g of x. All right, so that's going to allow us to replace that denominator with k. So I'm going to start rewriting here the limit. I'm going to leave our limit variable off for a second, and you'll see why. But our denominator here is going to be k. And I'll go ahead and bring down my g prime of x over here. That part's done. So the next thing I'm going to do is I'm going to do a little substitution. I don't want this g of x plus h in here. That's a little bit messy. So I'm going to solve my my equation here for g of x plus h, and we get that is going to equal k plus g of x. So I'm going to substitute that. I'm going to rewrite it as g of x plus k. And you might see where this is going at this point. With these two right here, it's starting to look like a limit definition of a derivative with k in there instead of what we're used to with h. I lost a parentheses here. That's not good. And then with the same equation here, we can solve for, we don't need to solve for. We'll just bring f of g of x down as it is. And as long as k is approaching 0, this is the definition of a particular derivative. So remember f of x plus h minus f of x. So the g of x right here is replacing the x's in that limit definition. And we'll be able to handle that. So the problem is we don't know if k is approaching 0. But if we think about what's happening here, k is the difference between, I'm looking at this equation right here, k is the difference between g of x plus h and g of x. And remember, h is approaching 0. So if h is approaching 0, this first function is getting closer and closer and closer to g of x, which means that that difference is getting closer and closer to 0, because as this gets closer to g of x, when we subtract g of x, that's going to get closer to 0. So, long story short, as h approaches 0, k is also approaching 0. Now, we don't necessarily know how fast k is approaching 0, but that doesn't matter. All that matters is we know that k is approaching 0. So with that, now we can rewrite this as a derivative that is not f prime of x, because remember we replaced the x's with g of x's here. So where we're used to seeing x's in our limit definition, that's replaced with g of x. So this is the derivative of f of g of x times g prime of x. And this gives us here what's called the chain rule. It gives us a way of taking derivatives of composite functions regardless of what those functions are. And the idea here is we're going to take the derivative of what I'm going to call the outer function. So we'll look at some examples in another video, but in a composite function, let's say, for example, the function, I need to use a color you can see a little better, sorry, sine of x cubed. This would be a composite function f of g of x if f of x is sine of x, so that's the outer function, and g of x is x cubed. So I would call this the outer function and this the inner function. So the idea is we're going to take the derivative of the outer function and keep the inner function inside, and then take the derivative of the inner function and multiply them. I'm also going to refer to these when I'm doing problems with the chain rule as mother functions and baby functions. So we think of the baby function being inside of the mother, so thinking like a pregnant mother. So the way I learned the chain rule, and this is a visual that hopefully would help you remember it also, is that we take the derivative of the mother, derivative of the mother and keep the baby inside, and then multiply by the derivative of the baby. And I know that sounds kind of funny, but if you think of that, so we have derivative of the mother and keep the baby the same. So g of x does not change in this step. So keep baby inside. And then we multiply by the derivative of the baby. So I will actually use these phrases when I'm doing the examples in the example videos, so you know what I'm talking about when I do that.